And Leah and everybody else for having me come up and even everyone today. It's great being here. So, like Mike said, I've worked for the past several years on a project with the SENS Foundation termed LysoSENS. And what I'd like to kind of go over today is a little bit of what we do, give you a quick overview, and then show some of the results that we've gotten throughout the year. So, most of the work we do is focused on the lysosomes. And most people think that the lysosomes are the recycling center of the cell. So old and damaged components get recycled so the cell can reuse them. But actually, there's a couple other functions that most people overlook. One is that the lysosomes are involved in phagocytosis, which is the uptake of particles or cells from the extracellular environment. For instance, this could be a bacteria. Lysosomes are also responsible for something called receptor-mediated endocytosis. So this involves the uptake of certain cellular components that the cell needs, such as cholesterol or perhaps iron. And of course, there's autophagy, which is the recycling of the cellular components. So all of these are very important parts of cellular function overall. And but the problem that we're trying to address is as people begin to get old, as people age, we start to see a decrease in the functions of these, or a decrease in these particular functions. And this is going to impact the cellular health and the organism as it ages. So why do we believe that the lysosome actually becomes impaired with age? Well, something we call catabolic insufficiency. Now, normally in the cell, we have a lot of different types of molecules and organelles that, just as a part of the normal metabolism, they become damaged. They become oxidized or glycated or cross-linked. But typically the cell has a pretty good ability to repair these molecules. Now, however, there is a small subset of these damaged molecules that kind of slip through these repair mechanisms. And what we think is happening is that this small subset of damaged molecules is accumulating. It accumulates at a very slow rate. So when you're 20 or 30, this doesn't really affect you. But by the time you're way past reproductive age, then you get to see some of the effects that you can associate with aging. So the prototypical compound that accumulates with people that age is called lipofuscin, or lipofuscin, it's not really a sense of how to pronounce it. And we really don't even know what it is. A lot of people say it's 30 to 70% protein, lipid. What we do know is very complex. It's probably very cross-linked, and it fluoresces. And it also accumulates in the lysosome. Some interesting things about lipofuscin, though, are that it accumulates at a linear rate throughout your lifetime. So it starts when you're a baby, you have it in your cells, and by the time if you get to be 100, you might be taking up 75% of the cytoplasmic volume of your cells in one of your motor neurons. That's a lot of the volume. Now, smaller amounts of lipofuscin are found in slowly dividing cells, and in rapidly dividing cells, there's almost none. And we think that lipofuscin actually accumulates due to recalcitrance and not failure of a specific lysosomal component. The theory is that this compound doesn't matter until after reproductive age. There's no reason natural selection should have come up with any means to degrade it. But we want to. So why should this matter for any of you? What are we trying to do by removing lipofuscin or removing other types of damaged components from the lysosome? Well, there have been a lot of studies done on one of the processes the lysosome is involved in, that's autophagy. And what you see here is a long list of genes. Each of these genes was thought to be related to autophagy. So a lot of different scientists did studies where they either overexpressed or inhibited these particular genes. And then they measured two parameters. One was autophagy, and they measured lifespan. And you can see in almost every single case, when they increased autophagy, they were able to increase lifespan. Now, all these were done in around C. elegans. Does this hold true in other organisms? Well, it does in the fruit fly. It does in mice. And whether or not it does in humans, well, that's still up for some debate. I guess we'll just have to see. So what else accumulates in the lysosome? Well, lipofuscin does. There's other forms of what people kind of term lipofuscin that are single molecules. A2E is one of them. And they're doing research on that at the SENS Research Foundation. I concern myself with mostly oxidized lipids, in particular oxidized steroids, and called oxysteroids. The one I've really concerned myself with is something called 7-keto-cholesterol. Most people know what cholesterol is, and this is a cholesterol molecule sitting in a membrane right here. Sodium keto cholesterol is almost exactly the same, except this is 7-KC down here. There's a little extra oxygen that's been added here due to reactive oxygen species or free radical attack. So it's just oxidation. And you see, this kind of demonstrates what 7-KC does. In the membrane, cholesterol kind of sits up like that. Well, when it becomes oxidized, it wants to sit like this. So it spreads these phospholipids apart, kind of spreads the membrane apart, and it can increase permeability in the membrane. So this is what 7-KC actually does in your cell. These are human fibroblasts here, and this is what they're supposed to look like. They're kind of long. These are untreated, no 7-KC added. And this is what a healthy fibroblast looks like. However, when we treat them with 50 micromolar of 7-KC, which is kind of a moderate amount, you see almost complete cell death. Now, what we're concerned really with here is heart disease. And in an atherosclerotic plaque, 50 micromolar of 7-KC is very doable. Actually, I think the highest level you see is about 100. Very advanced plaques. Early stage plaques, you probably have lower amounts of 7-KC than that. So this is the effect on cell viability down here. Obviously, the more 7-KC you have, almost complete cell death down here. These are just some controls that we ran. Now, that was 7-KC fed to fibroblasts. But fibroblasts, really, we don't think of those being involved in atherosclerosis. What we think of being involved in that is macrophages. So macrophages, as you saw in the video, they uptake oxidized LDL. Well, I just recently completed some studies to see what exactly does 7-KC versus oxidized LDL. So LDL is composed of many different components that could be oxidized. But what happens if we take regular LDL that's not oxidized and load it with 7-KC? So that's the only altered component. Well, what we see here is this is untreated. These are monocytes. And what I've done here is I've oxidized LDL. So this has a lot of different oxidized components. This is untreated LDL. This is 7-KC treated. And what you're looking at here is these little cells are undifferentiated monocytes. But kind of these unusual looking ones down here. These are what we call, this is a differentiated macrophage. This is what it would look like after it's kind of passed through your blood vessel wall. It's adhered, and now it's kind of taken up. And they get big because they're taking up lipid, they're taking up LDL and oxidized LDL. And this would be the wall. Now, just using regular LDL, you don't see differentiation like you do with 7-KC. Matter of fact, if you use this HOX stands for highly oxidized LDL. So I've really oxidized this in the lab and fed it to cells. You do see some of these macrophages that are differentiated, but it's to a much lesser extent than we see with just 7-KC. So this does tell us 7-KC is the target that we need to be concerned with. I was told this is a mixed audience. I don't know how technical people want me to get, but I will just tell you some key points here. 7-KC loaded LDL increases lipid accumulation as well in these macrophages. And actually what we see compared to other treatments, 7-KC normally causes about 50% greater retention in lipid in these short-term experiments I'm doing. So these typically only last like a week. Atherosclerosis takes a lifetime, not a week. So 7-KC could be having other more profound effects as time goes on. Phospholipids are increased. Free cholesterol, oddly, was not increased in the experiments I've done. And the effect persists when you normalize. This is kind of a proxy for cell size in experiments. Now, when you extend the cultures, if you do cell culture, what we can see is in almost all our treatments we get from cell formation. We haven't really determined exactly why that is yet, but in long-term culture, we may be getting oxidation of the LDL in the culture, which could be causing differentiation. That's one theory, but we're still trying to put this together and find out exactly what it's called. So how do we plan on treating all this? So we know 7-KC is the target. Do we have a strategy? Well, the first strategy is to actually increase the efflux of 7-KC out of the lysosome when we think it's doing its damage. And this is sort of the pathway that steroids follow through the lysosome. They come in through, as you saw in the video, as this oxidized LDL, or just regular LDL. Once they're inside the lysosome, an enzyme, lysosomal acid lipase, leaves the cholesterol ester, leaving just cholesterol and the ester by itself. Cholesterol is then absorbed by this NPC2 molecule, transferred to another NPC1, and then cholesterol is a very hydrophobic molecule. It can't exist just in, it's not soluble. It doesn't exist in the water. It precipitates out. So cholesterol has to be carried by something, or it has to exist in a membrane. So these kind of shuttle each other, kind of hand cholesterol off. Cholesterol is deposited in the lysosomal membrane. Now, if this is 7-ketocholesterol that's deposited here, this is where we could be having a problem, because then we would increase the permeability of this membrane, and that would upset the pH inside the lysosome, and when you raise the pH in the lysosome, enzymes don't work anymore. Okay? So then cholesterol kind of goes out of the ER membrane. There's another ORP5 enzyme that brings it to the ER, and once it's in the ER, well, we think we're safe, because then there's other enzymes that can act in 7-KC to reduce its toxicity. However, the key is there aren't any enzymes in the lysosome that can reduce 7-KC toxicity. They don't exist. So what are the enzymes that can reduce it? Well, there's one in the ER. Actually, this makes the situation worse. Okay? So this enzyme actually increases cell death. Okay? Because it's converting it to a more toxic form. Converts it to 7-beta-hydroxycholesterol. These other three can almost completely detoxify 7-ketocholesterol, but the cytoplasm and the ER. So the problem is, if 7-KC is coming in the cell or being formed in the cell in lysosome, well, that's where we need to act. We can't, unless we can get it out here, we either need to get it to these locations or we need to transform 7-KC in the cell. So our first strategy is mobilizing interlysosomal steroids. And we've got many different ways to do this. And we can just start with all those enzymes that I showed you in these pathways. We can try to upregulate them. Now, that may not work. You've got some other cytoplasmic sterol shuttles that can take perhaps 7-KC out of the membrane and transport it to the mitochondria and other places where it can be detoxified. And then we're also working with this thing called TFEB, or transcription factor EB. This is kind of a master regulator of the lysosome. It upregulates lysosomal biogenesis and also exocytosis. So we're hoping that TFEB can help with some of these problems with accumulations in the lysosome. Now, I was hoping I could come here today and show you the results of all these great treatments that I did, because I did these yesterday in the lab. This is a picture that I took in the lab yesterday. The problem that we have with the foam cell is that we get very low transfections. Now, a transfection is what we call the introduction of DNA in the cell. So if I want to test some of these treatments, this is how I normally do it. But fortunately, I found that only a couple of the cells, all these cells, actually uptook the genetic constructs. Now, the good news is these guys aren't foam cells. But the bad news is this probably isn't a very statistically relevant sample. So we're going to have to continue this work, look at other ways to get these constructs into the cell. If anybody here is an expert in gene delivery, please come speak to me afterwards. But we've got ideas and we're working on this. Now, I'd like to back up. This is some research I did before this. And we do have actually some ways to reduce 7-KC toxicity that we found besides interlysosomal transport. Now, one of these things is cyclodextrin. This is a small molecule. And what we found is that treating cells that are exposed to 7-ketocholesterol simultaneously with cyclodextrin dramatically decreases 7-KC toxicity. And this is kind of a long story, but there's several reasons we may not want to use cyclodextrin in vivo. But it is a good benchmark, and it does have some promise, especially looking at other types of molecules. So this is a picture. Now, if you remember the picture I showed you previously called the dead cells, it's the same concentrations as 7-KC, just add hydroxyprotein or cyclodextrin, and see almost no cell death at the same concentration. Now, option 2 is interlysosomal transformation of 7-ketocholesterol into a less toxic form. The problem is, like I said, that there's no enzyme that's targeted the lysosome that's capable of this. So what we had to do was engineer an enzyme to go to the lysosome that could transform 7-KC and reduce toxicity. And this is showing the results of a paper that we published earlier this year. And we were able to take a particular enzyme that we isolated from the bacteria. We were able to introduce it into the lysosome and this is that particular treatment. Now the axis here, it doesn't indicate very well, but the higher the number, the greater the cell viability, or the greater the number of cells that are alive. This is our control. It even surpassed the control. That's not uncommon. It just provides something more that the cell needs and accepts. But what we see here is that 11 HSD I showed you did what it was supposed to do, it decreased cell viability. And we actually see a pretty significant increase in cell viability up through 50 micromolar, which is normally kills almost all the cells. You still see some alive. This is a picture. So this looks a little bit different than cyclodextrin, but you can tell these cells are obviously using nice healthy fibroblasts. And what this actually is, this is the construct I used. I used this is a LAMP1 protein, which is normally located in the lysosomal membrane. I kind of deleted a portion of it. I left the targeting signal here, so this particular insert would make it to the lysosome. The little problem we had is these are normal fibroblasts. They look nice and healthy. We did see morphological changes in our treatment, and the reason we think this happens is because this particular enzyme just doesn't degrade 7-KC. It also acts on normal cholesterol. So this is one of the problems that we're addressing. Now, interestingly, I used LAMP1 was that membrane protein I used to target 7-ketocholesterol. That ended up having a nice protective effect as well. And come to find out, LAMP1 is involved in exocytosis, and LAMP1 is also involved in cholesterol homeostasis and resistance to apoptosis. So we're not sure which of those particular functions is causing the increase in cell viability, but this is again one particular line of treatment that we may be able to use to protect against that KC toxicity. And this is just another slide showing even higher double concentration of 7-KC and all these different treatments. Normally you wouldn't see any live cells. In each of these treatments, we do see some live cells. Now, that's going to wrap up what my work is, but I'd also like to kind of showcase a little bit some of the work that we're doing at the SENS Research Center on a compound called A2E, which is what I was talking about, is a form of glycofusin that accumulates in retinal cells, and they think is responsible for age-related macular degeneration. What we're seeing here is just kind of an illustrative slide showing this is what you see fluorescing down here is A2E. This is just they synthesized it at the research center. They fed it to these what they call RPE cells, and A2E has accumulated in these cells. This is a lysosomal marker, and the yellow is showing that these two things are in the same position, so they're localizing together in the same place. Now, what we're showing here is an enzyme that we have identified at the research center is capable of degrading A2E. And so A2E, this is showing cells that have not been treated with the enzyme. This is showing cells that have been treated with the enzyme. And what you see is almost complete disappearance of A2E in cells that have been treated with this enzyme. You see here the merge, so I don't think there's any yellow in here. So all the lysosomes that this enzyme made it into removed, almost all of it. It looks like all of A2E. This is just one of the exciting things that they're looking at. Okay. Some of the, just briefly, some of the current and future projects we're working at Rice University. We continue to develop these foam cell models, looking at gene delivery methods. We're looking at methods of, increasing sterile efflux and transformation. We're looking at, different methods of altering enzymes to increase their ability to modify 7-ketocholesterol. And we're also working with this, the complex glycofusin. We're starting a new project that involves that. We're just kind of getting that off the ground, looking at ways to generate cell-based models so we can test particular treatments and get rid of them. With that, I'd just like to acknowledge my collaborators at Rice and Baylor College of Medicine, as well as the whole SENS Foundation, specifically people who have been